Gnanam paramam dheyam. Knowledge is supreme.
Recall classical mechanics. When you had equations of motion, I am sure you would have seen this. In classical mechanics, dA by dt is del A by del t if it has explicit time dependence. If you look at operators which don't have explicit time dependence, I can forget about this. Plus Poisson bracket of A with, you have done this in classical mechanics. What is the expectation in quantum mechanics? Ehrenfest's theorem tells us d by dt of matrix elements or even expectation values should be expectation value of del A by del t plus Poisson bracket becomes commutative bracket with a 1 over IH cross. Okay. So, this will become a commutative bracket, matrix element, there will be probably a 1 over IH cross here. This is what is my kind of a guess. I am not proven now. We would like to prove so that we are consistent with Ehrenfest's theorem that the familiar equations of motion which you see in classical mechanics should be reproducible for the matrix elements in quantum mechanics. So, this matrix element, as I said, this A is a function of t. How you get A to be a function of t in Schrodinger picture is the states are functions of time. In Heisenberg picture, operators are functions of time. So, when I do the d by dt, I will either do d by dt on the state in Schrodinger picture or I will do d by dt on the operator in the Heisenberg picture, and I need to derive this. Okay, so that is what I am going to do next. This is just to show that everything is tightly consistent. You don't, whatever you get in classical mechanics, when you go to quantum mechanics, this is your expectation. Are we consistent? So, I have stressed the fact that either you work in Schrodinger picture or Heisenberg picture, both will give you the same physics. Now, let us look at Heisenberg's equations of motion in Schrodinger picture. So, you take the time derivative of a matrix element, d by dt of this. So, in Schrodinger picture, as I said, the states evolve in time. So, we will try to put del by del t on the state. AS is not affected, but AX could get affected if it has an explicit time dependence. If you don't have an explicit time dependence, this term you can put it to be 0. If you have t times xp plus px or something, then there is an explicit time dependence. Okay, so this term in general is possible if there is an explicit time dependence. And then the last, the ket state. Okay, then what next? What will you do next? Use your postulate for the equation for the time evolution of the state. So, del by del t of psi of s is h on the same ket, right? What is this? Right? This is from this place only we derived the unitary evolution. This is the Schrodinger equation for the state evolution of the state, time evolution of the state. We have this equation which ultimately gives us for time independent potentials. You could show that this is nothing but this we did, right? So, we need to substitute this. We need to substitute this in your simplified matrix element and see what we get. So substitute for this. Hamiltonian is Hermitian. So this will also give you, so when you do it on the bra, what happens? Will there be a negative sign or no? IH cross del by del T on phi s if it is H on phi s. You take the dual. So dual will give you the bracket, the bra, the dual vector. IH cross will become minus IH cross del by del T. Is that okay? And Hamiltonian H dagger is H. So you need to substitute this and this in the first term and the last term. Okay, substitute that. What do you get? Slowly it's coming, right? You get a H, you get a minus H, and the order matters. HA is not same as AH, so you have to be careful. And will we get a commutator? This is a minus sign because of this. Simplify this equation, all of you. What will you get after you simplify? So the time derivative of this matrix element of an A operator turns out to be the matrix element of, if there is an explicit time dependence, you have a partial derivative of this A operator, plus the first term would have given you a minus HS AS. This term will give you a AS HS. What is this? This is nothing but the commutator bracket. So we have tried to prove what you have seen in classical mechanics in the Schrodinger picture, that it is the matrix elements which obeys exactly the same equation with the Poisson bracket replaced by the commutator bracket divided by IH cross. This is what I was saying. This is your expectation and we have verified. But as a check, we should also redo the same thing in the Heisenberg picture also. We did this in the Schrodinger picture, but we should also redo this in the Heisenberg picture to make sure that the same physics equation is got even in the Heisenberg picture. So let's take that the operators which we are going to consider don't have explicit dependence on time, which means del of AH by del T is set to 0. Okay, there is no explicit time dependence. The partial derivative of this A operator with respect to time will set it to 0. You have to show, we have already seen in the Heisenberg picture that the matrix element time derivative is explicitly the commutator bracket. This we have seen in the last slide. And this is what I said, that if you try to recall how a dynamical variable which is not explicitly dependent on time, when you do it in classical mechanics, you will write dA by dt as del A by del x into del x by del t plus del A by del p into del p by del t. There is no time dependence, explicit time dependence here. All the observables or all the dynamical variables in classical mechanics is dependent on phase space coordinates. Phase space is x and p. You could have a time also, but if you had that time, you will have a partial derivative of A operator with respect to time. That I didn't put because I am just taking A to be only dependent on x and p. When I say it does not have explicit time dependence, this is what I mean. It has an implicit time dependence coming from the time evolution of this phase space. There is no explicit time dependence. And use this Hamilton's equation to rewrite things, and then you see that it is nothing but a Poisson bracket. This is just to recall. And we see the similar thing happening here for the matrix element, which is what is called as the iron first theorem expectation. So notice Poisson bracket becomes commutator bracket in quantum mechanics, and equation is on quantum mechanics, matrix elements. So this is nothing but your iron first theorem. So far we are still in Schrodinger picture. We have not gone into the Heisenberg picture. This equation, which if you see the classical mechanics, they call it a Heisenberg's equation of motion. So that is this equation is called Heisenberg's equation, and this we have verified in the Schrodinger picture. The classical mechanics equation becomes in Schrodinger picture on the matrix element. So now we will do the same equation in Heisenberg picture. In Heisenberg picture, when we take d by dt on this matrix element, interestingly the states don't evolve in time. So what evolves in time is operator. So that's why this matrix element is explicitly dAh by dt. How do we do this? You know AH, the explicit form. AH is nothing but U dagger AS U, right? You can first do, if there is an explicit time dependence, you will have a del AS by del T. Otherwise, you have to have du dagger by dt. So if you try to do that, what will happen? There will be a Hs coming up from there, right? Shall we do that? Let's do it together, and then maybe then we can flash this slide. So AH of T is U dagger T comma T naught AS U of T comma T naught. D by dt of AH is du dagger by dt AS U plus U dagger, I am just suppressing all this T comma T naught, okay. U dagger AS du by dt, right. What is du by dt? Minus I by H cross Hamiltonian times U. Du dagger by dt will be plus I by H cross U dagger. Here in this particular case, U is a function of Hamiltonian. Whether I put this side or that side should not really matter. It is very crucial. Yes, quantum mechanics is very crucial. You have to keep, but where I put this is very important. I can't put this H. I have to, when I substitute back here, I have to keep that, because you can't cross the AS. Okay. So you can't cross the AS. So can we simplify that, substituting this here? Is that right? Do a couple of things here. Tell me what you can do. I by H cross. You can write this as, what is this? AH. Similarly, I can swap this H and U and write this as AH H with a minus sign, and here you will have allowed. So what happens? Both are equivalent. The beauty in Heisenberg picture is, since the operators are functions of time, I don't need to too much worry about matrix elements here. I can focus on, because the states don't evolve in time. This equation will be exactly same as what you see with Poisson bracket in your classical mechanics. in the Heisenberg picture. But you have to say that you are in the Heisenberg picture so that everybody knows that the state vectors don't evolve in time. The putting the matrix element, you can put it, but those are frozen states. They don't evolve in time. Ironsworth's theorem is still not violated, but we have tried to rewrite in a different viewpoint, which is a Heisenberg picture, where we wrote operators as functions of time, and the equations are exactly similar to what you see in classical mechanics as an operator equation with Poisson bracket replaced by the commutator bracket over IH cross. Okay, so do the derivatives, that is what I did now for you. You can go back and sit with this and do this, and you can show that there will be, if there is no explicit time dependence, then you can try to forget about this first term. If there is an explicit time dependence, then this is an operator, this term is the operator in the Heisenberg picture, right. What is the operator? Del AS by del T operator with U dagger U is what I will call it as a Heisenberg picture operator. So I ignored this term for simplicity, saying that we look at observables which have no explicit time dependence. Even if you have an explicit time dependence, you can write an operator equation for the time derivative of an operator as the commutator bracket, and you can have a Heisenberg picture operator where del AS by del T is a Schrodinger picture operator. Heisenberg picture operator means you will insert a U dagger in front and U on the. So any operator which I give you, suppose I write AS with subscript H, this should be read as this is the mean. Okay. The subscript H means I have to write the Heisenberg operator, and I can write it like this. So wherever you get this, you should replace it. So that's the theme of these two pictures, and we'll have some problems on it, on these two pictures, how to relate one to the other. So the thing is, if you want to look at stationary states, Hamiltonian on, let's say, stationary states which are EI on UI, you can always show that any linear operator, the matrix element, what will this be? It is UI Hamiltonian A operator UI minus UI A operator Hamiltonian on UI. This will be EI minus EI, right? Y star, but Hamiltonian. So this is going to be 0, right? So the commutator bracket of this Hamiltonian with A on the stationary states of the Hamiltonian, they are always 0. So many times these things will help us to try and look at time derivative of the operator very nicely, some of these things. The other thing which I was trying to say is, if you can write some other operator as commutator of H with A, okay, so that was the question in that assignment. Show that your momentum operator, what was the Hamiltonian given? Somebody? Something I think, B of x. momentum operator can be written as up to some factors. Let me not worry about it. It's proportional. Once I write some other observable as a commutator of the Hamiltonian with something, that helps me to trivially say, what is this? 0 by this argument. Take your harmonic oscillator for example. Harmonic oscillator, if I ask you to find what is the average momentum, what will you do? Expectation value of momentum. What will you do? In the wave function formalism, what do? Let's say the particle is in the ground state. What would you have done? Dx psi 0 of x, p operator, psi 0 of x. What you would have done? Equivalently, this can be rewritten as the z0, u0, p operator, u0. This explicitly if you do using the Hermite functions, you can show that this expectation value is 0, right? But now instead of doing it this way, I have tried to say that this is same as u naught Hamiltonian for the harmonic oscillator is up to some factors. I am not worried about those factors. P squared over 2m plus half kx squared. Let put m to be 1 and k to be 1. Then you can always write Hamiltonian with x. Let's do Hamiltonian with x is, which one will contribute amongst these two terms? P squared over 2m alone will contribute. And what will this be? 1 by 2m into 2 into p operator. So essentially I have shown that 2IH cross. Yes, thank you. Yeah. Excellent. So essentially what I am trying to say is, instead of doing this long winded calculation, I can exploit whether this observables can be written as a commutator bracket of Hamiltonian with something else, which can be any linear operator. This we have shown it to be 0. If I can write my momentum as a commutator, it is 0. Same argument, instead of working with this, you could have worked with, if I want to find what is the expectation value of x operator, you can show this to be proportional to someone. This is also 0. I am just trying to say the power of using this Dirac notation, the commutator bracket are, it's completely invisible, but lot of things are happening. Okay, so let me stop here.